Alrighty, good afternoon, and my name is Mikulski, and I'll be diving into cellular technology. Exactly. A lot of people just conflate cell tech to magic, and I'm here to try and demystify this magic, even though it is magic, and sometimes I ask why it works, and there are some very smart people behind why this works. So first off, a little bit about me. Well, I'm just someone who has done a lot of things and a lot of weird things. I actually did manage to set up a cellular network. It was meant for ISTS like last year, but the government stopped me because the government is very picky about certain frequency spaces, such as which being cellular. I also drive cars. Yeah, that's fun too. So anyway, wake up people. Come on, you don't understand. But nah, I laugh at this every time I see it because it's just like the whole like conspiracy theorist thing. It's just funny. But anyway, let's start diving into this. First things first. Let's talk about what this presentation is and what this presentation is not. What I aim to do here is just to be a general overview of a very high-level, broad description of what cellular tech is. This is not meant to be a dive-in and to be like, here's the frequency ranges and the bandwidths and like how these protocols and systems actually work. No, I'm not going that deep. If I was to go that deep and across all 5 generations, we would be here for at least a couple of hours, and that's not the intent here. The intent here is just to start going over like the black magic that makes our cell phones work. So, first things first, what is a cell phone? Well, if you really think about it, your cell phone is just a computer. It's just a computer with what's called a cellular modem inside of it, or modem standing for modulator demodulator. It's the same thing that we have in all our houses that normally is connected to a coaxial line from our internet service providers. It just modulates and demodulates signals to be interpreted and presented in another way to whatever system's on the other side. In the case of our home internet, it's designed to turn it into signaling that can travel over coaxial lines, versus with a cell modem, it's designed to be transmitted over the air on RF. So, then there's the idea of what is a mobile hotspot. Well, it's just a router. It's just a wireless access point that has a cellular modem. Again, it's just another way of just connecting to this broad network. Cellular tech can, in essence, be thought about as just a giant network. It's just something that connects technology. It's something that connects surprisingly over IP. But we can find some common ground into some already existing ideas that we know about from modern Wi-Fi tech. So handoff and roaming, again, cell sites which we'll touch on what those are, can be thought about as just wireless access points. And when moving between geographic locations, whether it's just in a building or whether it's across miles, there's got to be some form of handoff or roaming when going between places, so that way your device knows to connect to the same network, but to a different physical device. Next is MUMIMO, or multiple user multi-input, multi-output. This is a concept that I forget what the RF term is, but it just abuses an RF effect to increase throughput on devices. So let's talk about, pretty much start diving in. So everything's a generation. So when you hear terms of like 4G LTE or 5G, 3G, that just defines a generation. It's just pretty much defining a set of standards, a set of protocols for that time period. Technology and innovation is what always drives these generations. So like 3G, some innovation happens and suddenly they're taking that tech and innovating on it and pushing out 4G. Same goes for 5G. That's what happens here. So welcome to the madness. This is a chart, surprisingly gotten off of Wikipedia, of just defining where everything exists. As you can see, it can kind of be considered a mess. For those of you who were here last spring when I was working on a cell network, you may remember the ramblings of a madman and talking about like, oh yeah, so cellular is just a protocol stacked on top of another one, side-loaded and alongside another one, and thus cell phones work. Yeah, this pretty much explains it. So all the colors are representative, and I don't know why it's cut off, but red is 1G, orange 2G, green 3G, light blue 4G, and then dark blue purple 5G. So these are all the protocols that generally exist in those spaces that make it all work. A few of these that we're going to be talking about and diving into is CDMA 2K or 2000. We're going to be talking about GSM. We're going to touch a little bit on WiMAX, UTMS, HSPA+, LTE, just to name a few of what I'm going to be talking about throughout this time. So first off, first generation, it's where we all started. Started out in the 1980s out in Japan, a telephone company, and I know I'm going to mispronounce it, called Nippon Telegraph and Telephone, NTT. They're the ones that made the first commercially available 1G network. It was all analog based, so it was definitely an interesting time. Not much to touch on there because we didn't enter the digital age yet. Now we get into 2G, the second generation. So now things start getting digital. So first off, there's a couple things that we need to talk about first, which is GSM, CDMA, TDMA, GPRS, and EDGE. These are all protocols and standards that exist within the 2G spec. So 2G kind of defines the broad capabilities where now we start diving into more protocols and like standards within this broad generation. So GSM, this is kind of like the parent standard. This is what exists at the top that defines a lot of the scope for what 2G is all about. GSM shows up later. So it just kind of says like, hey, here's like frequency space, here's multiple access, here's your multiplexing, here's how you define your network architecture. That's all generally covered under GSM. So then this CDMA and TDMA, or code division multiple access and time division multiple access, these are from what is called multiplexing. What is this really? So it's defining how you access a system with multiple users. So if we talk time division multiple access, TDMA, which was commonly used in, if I remember correctly, Europe and Japan for 2G, it's where you get allotted a time slot. So everyone communicates pretty much across the same band, but you're given a time slot. So when you're doing communications, you either have to wait your turn, or if it's your turn, you put all your data into your time block, and then you send it off, and then wait your turn again to send or receive more data. Code division multiple access is where the frequency spectrum gets a bit broader, but you're given a certain bandwidth, and then it's more about just the frequencies and how you're modulating on those frequencies for code division. Now, a lot of this has still been happening over analog, but we still get a bit digital, because now we're in the 2G phase where we're sort of transitioning away from 1G, and we're starting to get a bit more digital. So this is where GPRS, or the General Packet Radio Service, comes in. This begins to introduce IP into the mix. So now we can start communicating with IPs. So you'll get an IP address, or your carrier gets an IP. It varied between carriers during this time, so no real definite answer from me at this current stance. But it allows you to, like on this Sony Ericsson, access Wikipedia or the internet from your cell phone. This was revolutionary, because it's like, from this device in my pocket, I can access the internet. So interesting. But now we get into Edge. So we're like, hey, we want to go faster. So Edge comes in and just is a standard and a spec that starts to push the speeds. So from Edge, we can get to 64 kilobits per second. At the time, that was fast. One thing I will note, and this is something that I forgot to mention earlier, but it's just a fact, is when you start actually doing your own research, you'll be like, oh, a 2.5G or 2.0G or, as I'll touch on, 3.0, 3.5, 3.9G. So as these standards got introduced, they in essence started adding this decimal notation, but for sake of keeping this high level, I'm just not going to touch on that. Anything that exists in that generation, I'm just calling it in, no matter whether it's the 2.5 spec or the 2.9 spec. But anyway, side note aside. So next in 2G is where the introduction of SIM cards come from. Now let's talk about what a SIM card is. So there was an interesting discussion on the RITSec Discord about SIM cards. And it's like, oh, it's a form of DRM, which depends on how you look at it. Kinda, not really. But a SIM card is pretty much your subscriber identity module. It's a smart card. So like, if you look on your credit cards, your debit cards, you see this little chip right to one side, sometimes the left, sometimes the right, depends. But that's pretty much just a computer. You have a computer in your credit card that stores your information. Smart cards are interesting because they're mainly used for cryptographic functions. So they can store private keys, they can store RSA keys, whatever private information can be stored to personally identify you. Now, where does this come when it comes to cell networks? Well, this contains your identification and authorization keys and also your network information. So when you get a SIM card for like Verizon, it has keys on it that identify to you, to your account, that card to your account, and then it maps to you as the user and to your device. So that way, the cell carrier can know and be able to identify who you are. Your phone is registered to your account, which is mapped to your SIM, and it's all just mapped together in one bundle, and it gives you access. That's in part handled by your SIM card. Fun fact too, since they're technically computers, smart cards can actually run Java. That was the most popular language to run on it, so you can run little Java applets. And for back in the old days, you could store contact lists on your SIM card. I think you can still do that now, but because of just wide amount of storage, it's not really needed anymore. It was mostly used back in the day when you couldn't store contact lists on your phone. So when you went to switch to a new phone, you just take the SIM card out, pop it in a new one, there's all your contacts again. 3G. Now we're starting to get a bit more to the age of where we are now. Like when the iPhone came out, it was connected to 3G networks. So we're in the third generation now. Still uses a bit of GSM. You see a bit of GSM still showing up, but a lot of it is greatly modified and brought to new specs and new standards. So what do we have now? We have UMTS, the Universal Mobile Telecommunication Standard. This is, again, that, like GSM, this large overlay protocol or set of standards that says how the network's defined, what's the frequency range is. It defines everything. CDMA 2K, it's just code division multiple access with some modifications to allow for faster data rates and better management of frequency space. Next, we get into HSPA+, or Evolved High-Speed Packet Access. This comes off of high-speed packet access, which all these are just standards and specs that define a way of transmitting data faster. It's all about just data throughput and being able to send data over a cell network faster. And that's all it is, really. So what this leads us to now is 56 megabit per second. So now we're starting to see regular sets of speeds. Next, For 4G, fourth generation, this is where long-term evolution comes in. So when you see 4G, 4G LTE, technically LTE comes as a result of 3G. It's kind of like 3.95, but it wasn't really implemented in the 3G spec. It was more or less fully fleshed out in 4G. But anyway, it's more or less the overarching broad of like, hey, this is 4G now. But what's interesting about LTE is because it was more or less a complete redesign of cellular spec, what happened here is inside the 4G spec, they're like, hey, for all of you on this UTMS or GSM networks, here's conversion guides. So for carriers like AT&T, Verizon, T-Mobile, Sprint, when they're on their 2G and 3G networks, GSM and UTMS, in this LTE guide, there's guides and spec and more or less general recommendations on how to take their networks in these states and convert them over to LTE networks. So, WiMAX, or Worldwide Interoperability for Microwave Access. Probably most of y'all have never heard about it. I didn't really, not until I was building a cell network, and I'm like, what's this WiMAX? So it turns out WiMAX, this mostly comes from the Eastern Hemisphere. That's where this is mostly based out of. WiMAX and the WiMAX organization, I think it's called the WiMAX Council, is founded out of 2001, all about building up WiMAX. But the thing is, it never made it over here to the US. We mostly just adopted LTE, and didn't have any problems with it. We didn't really see the need or have the carriers who wanted to implement WiMAX in the US. So that's why it's just not really heard about. That's why everything we have is LTE, at least for fourth generation. So the thing with WiMAX is it technically does exist in the US, in Alaska, by AT&T. That's about it. So when 4G was being built, there were considerations being made. They're like, hey, this should be able to stream HDTV, gaming, video conference, all just stuff that we see and use on a daily. And those were all considerations for implementing a fourth generation network. But other than that, it's just faster speeds, greater reliability, more sites, and just general better architecture. Fifth generation, the buzzword capital of cellular, as that's buzzword central capital. The reason why I say that is a lot of times you hear buzzwords about, oh, it's going to be like this 5G, it's 5G IoT, which, yeah, but you could have done IoT with 4G. All you do is just slap on a cellular modem, or like from a company like Sierra Wireless, buy a modem router combo unit and just plug it in via Ethernet. That's all it took. I mean, I've deployed Sierra Wireless modems a couple times in previous jobs. It's no need to come out in 5G, but 5G has been the big push because very high throughputs, very high speeds, very high network capacity. Also a bit more reliable, mostly due to multiple sites being put up because, again, due to the frequency space that it's at, you need more towers because going longer distance and penetration through concrete, other types of walls, materials is very low. So you need more sites to be able to build up more reliable infrastructure. But anyway, 5G mostly, when you look at it without all the like corporatized buzzwords, is just faster speed, higher reliability. It exists in a higher bandwidth space, and it's just another improvement over 4G. Now, due to the frequency space, there is still concerns about health and aerospace, so like mostly aviation. But at least as of right now, nothing negative has come out in either of those spaces. I could be wrong, but based on just my research into 5G, I've seen nothing really conclusive. So in a sense, just 5G is meant to be like this whole push into automotive and IoT and everything else, but it's nothing that couldn't have been done previously. It's just I haven't been able to find why 5G is the core of all this, but it's just faster throughput and greater reliability and faster speeds. So, summary. Every generation going forward has been a push for more people, more speed, more reliability, more use. It's just been a push to improve the capacity and the ability of these cell networks. That's all these generations leading up to has created, is just bigger and better networks for all the tech that we're trying to put on these networks. Quick aside. And this is about your phone. So going back to the SIM card thing and SIM locking, let's say you're in an emergency situation. Let's say you're out in the middle of the woods, or you're in a place where you don't have, like, you use Verizon, but you only have signal or coverage from T-Mobile, and you're in an emergency situation. Well, your phone in an emergency situation will reach out and be like, turning up its gain and being like, hey, I need a network to connect to because I have an emergency. I need to route 911. It will route 911 because of federal regulation about how emergency calling should be done. So you're in a T-Mobile area and you're on Verizon, but you have an emergency. It will connect to that T-Mobile tower and route your 911 call. So, all this talk of cells, what's a cell? Well, a cell, whatever your biology class may have taught you, a cell is just a geographic area that is defined by cell stations, or base stations, or cell towers, whatever you want to call it. So, it's just a geographic area. So, right now, existing in here, in this geographic space, if we were to look at a cell map, we would see that we are actually on the cusp of a few towers. So your phone is always when you see signal strength, your phone is always in communication with towers, but your signal strength is defined by the tower that it has the best connection to, the strongest connection to. Your cell phones will always search for the strongest connection. So that's the closest tower, or that's the tower with the clearest line of sight. That definition of what's the best tower comes into a lot more of RF engineering and understanding how radio works. Infrastructure. Note, this varies based a lot on generation. It tends to change from generation, but this is an image taken from the Osmocom project, which is an open source implementation. I'll touch more on that in a minute, where it shows pretty much an example backend. So, you have your base station cell sites, or your BTS, base transceiver station from 2G networks, or Node B, E Node B, G Node B for your 3G plus networks. So this is pretty much what exists at the cell sites, or the base stations, or the cell tower. So when you see those giant cell towers with these like rectangular white bars sticking off the end, that's the antenna. But that routes all the way to the tower to a facility, like at the base of the tower or just a few feet away, that contains the BTS or the Node B. So that's the end that actually drives this antenna. Then you have your BSC, or your base station controller. This is what manages a lot of base stations. So a base station will go to a BSC and be like, hey, what am I supposed to do? I'm alive, I'm online, but how do I actually do a thing? Thing being provide coverage. So that's up to the base station controller, which is connected to the BTS or Node Bs actually go with the HNBGW, which is just like a base station controller, but it's more for modern stuff, more for modern generation, so 3G plus. Anyway, next we get to the HLR, or the Home Location Register. This is like the subscriber database. So like all cell carriers have at least one of these, and it defines you. It defines what your authorization keys are. It defines your number. It defines everything about you in context to that network. So that when you connect, the system is like, hey, it's just a database. That's all you have to think about it as, is just a database. It's like, hey, does this user exist here? Can they connect to me? And then it's like, yeah, they're here. Give them, they have this phone number. They can connect. Next, the MGW, or the Media Gateway. This is more of a conversion system. It's more about handling conversion and encoding, decoding, and transcribing. That's just the sole purpose of the Media Gateway. In the MSC, the Mobile Switching Center, you can think of this as like the core switch and core router of this network. It's defined as in, okay, I want to terminate a call. I want to call, let's say, a landline. Okay, I call. Then the Mobile Switching Center is like, okay, he's dialing this number. Does this number exist on mobile networks? No. Okay, so then it proceeds to route it to the public switched telephone network, PSTN, so that then it can route to landlines and over the wire. Or if it's a wireless device, so another cell phone, it's like, okay, you're a wireless device. So then it begins doing all its back-end routing to route it back to a HNBGW or a BSC to be like, hey, we need to go wireless again. So the Mobile Switching Center is just the core, and it's what controls switching and routing throughout this network. Okay, quick little disclaimer, because this is where stuff can get a little spicy. I'm about to talk about ways that you guys can go about setting up cell networks. Don't do it unless you have permission. Don't do it unless you understand what you're doing, because one, you can interfere with pre-existing cellular infrastructure. So you can interfere with Verizon, you can AT&T, and people in this room. The FCC doesn't like when you interfere, especially with cellular, because emergency response and first responders sometimes rely on this infrastructure. Don't. Just don't. If you can run it in Faraday cages, that's where I did it. The only time when you can start broadcasting publicly outside of like a Faraday cage, especially on cellular bands, is if you go to the FCC and you get what's called an STA, or Special Temporary Authority. What this means is it's a permission from the government where you tell them your frequencies, your equipment, you tell them everything about your setup, where you are, and you have to have an FCC ID or an FRN, FCC registration number, that maps it to you, that they give you the authorization to run this unit, so that then they have a throat to choke if anything goes wrong or you start interfering, but it also allows them to keep track of what's going on. So if you want to do this, do it in a Faraday cage, or get permission as long as you can understand what you're defining in this STA. And then you have to wait for the speed of government. Anyways, open source projects. The community really was able to build out, and there are 3 very popular projects that go over open source cellular telecommunications. That would be the Osmocom project, SRS RAN, and Open 5Gs. Open 5Gs is the newest kid on the block, as it's only designed for 5G infrastructure. So let's talk about SRS RAN now. SRS RAN stands for Radio Area Network, and it's a 4G LTE implementation for cellular networks. Osmocom, you can think about it as the OpenStack version of cellular. Everything is broken down into its own service. So if we go back to that infrastructure diagram, this image was taken straight from the Osmocom project, and everything is its own service. Granted, you can run a few of those services on the same host, but everything's its own service. So that's why I call it like the OpenStack of cellular, because that's what it is. It's a bunch of services that people have written to build open source cellular infrastructure. Now, when I was building the cellular network for ISTS, I used Osmocom. I built a GSM network, so 2G, 3G, and actually kind of got it working. I was actually quite happy with the results. But yeah, there's a bunch of open source projects, and it's great. It allows you to truly understand more on the backside of what cellular telecommunications is. Honestly, when you think about it, even though it's a lot very IP-based, cell tech is actually quite interesting, and just diving in through the projects and seeing how they work on the back end, pretty cool. Now let's start talking about some attacks, because this is a security club. So what's different? What's the same? Well, what's different? RF communication and mostly just authentication mechanisms and identifiers. That's what's different, because if you think about it again, it's all just wireless comms, so kind of like connecting with Wi-Fi. You still have a computer in your pocket, your phone. You can still do denial of service. There's impersonation, injection, RCE. Like, who remembers the text message that can crash an iPhone? Yeah, the text message that can crash an iPhone. So that's an example that could technically be deemed an attack through a cell network, because you're sending a message, an iMessage or a text message, to someone with an Apple device, and you're sending this string. It's just like sending an input and getting an output on someone else's server or device. So when thinking about attacks on cell networks, you have just to think about it kind of like how we are now. Like, yeah, it's this big magic system that works, but in the end, it's just like networks as we know, just different tech for a different purpose. So this time it opens up to RF, so you can start listening in with like SDRs and doing some funky radio stuff. So let's start talking about what is a popular and hot topic, IMSI catchers, otherwise popularized by the Harris name as a Stingray. So this is meant to be a man-in-the-middle attack. Remember back to what I said, where your phone will search for the strongest signal as a tower. That is what a Stingray does, is it acts as a tower. So if someone was to set a Stingray right here and then turn it on, suddenly everyone's phone would be like, wow, there's a tower right nearby. I'm going to connect to it because I can get a strong signal. It'll attempt to connect. And then the Stingray or IMSI catcher will relay that back to legitimate cell towers. So the Stingray will be like, okay, I know what's around me. I know what legitimate towers are. I'll relay traffic to those towers based on carriers. So that's what an IMSI catcher does. What it also does is it attempts to do downgrade attacks. So it will attempt to be like, oh, you're in 4G LTE, let's downgrade you to 3G or 2G GSM, to then begin to strip away some of those security protocols. Because again, you may go out into very rural areas where the infrastructure hasn't caught up with the times. So while we're all here in our 4G infrastructure, 4G, 5G infrastructure, maybe out west there wasn't as much of a push for an upgrade. There wasn't a user base, because remember, these are all private corporations. So they just haven't upgraded the towers, and they're still running 3G, 2G GSM. So your device still needs to be backwards compatible to connect to it. So that's in part what an IMSI catcher is abusing. It's abusing that backwards compatibility in knowing that, hey, not everywhere is at the same spec, so we don't have to worry about this. So it'll attempt to downgrade. So it can also be used in tracking. That's when you start doing IMEI and IMSI numbers. So those are two identifiers on your phone, an IMEI and an IMSI number. So it can just be used also in tracking applications, but that just goes down a whole nother privacy rabbit hole. So that's cell tech in a nutshell. Here are some resources. The reason why I list Wikipedia first is because it's just like, it's got links and it's got a bunch of terminology that you can do deeper research in. nickversusnetworking.com. So this is a guy out of Australia who just plays with telecommunications. It's honestly where I learned a good portion or a lot of setting up Osmocom for GSM and just telecom in general. The Osmocom official project. They got some great resources on talking about setting up their stuff and general cellular terminology. And then the NIST page for all the attacks and possible threats. Any questions? Thank you.